So, in the previous lecture, we have started to find the claims using Fourier series. Okay, so we have got the summation of 1 upon n square, that is going to be pi square by 6. We have got the summation of minus 1 raised to n plus 1 upon n square, and that we have obtained to be pi square by 12. Also, we have obtained the summation 1 upon 2n minus 1 bracket square, and that is going to be pi square by 8. So this way we have obtained the different series using the Fourier series. Now we'll see some more problems based on this Fourier series. So let's have a problem based on Fourier series. I hope my screen is visible to you all.
Yes, sir.
Okay, that's great. So we'll go for the another example. Find Fourier series function for f of x is equal to root of 1 minus cos x defined in 0 to 2 pi. Okay, so we have this function f of x is equal to 1 minus cos x, and then we have to find out the Fourier series for this. Uh, so the solution. Okay, let we have f of x is equal to root of 1 minus cos x. Okay, p defined in 0 to 2 pi, and hence we have is QL is equal to 2 pi. So we get L is equal to pi, and once you have L is equal to pi, then we can write the Fourier series expansion of f of x is given as. So we have here f of x is equal to a0 plus summation n running from 1 to infinity an cos of nx plus summation n running from 1 to infinity bn sine of nx. Let it equation 1, where a0 is 1 upon 2 pi 0 to 2 pi f of x dx. An is equal to 1 upon pi 0 to 2 pi f of x into cos of nx dx, and n is equal to 1 upon pi integral 0 to 2 pi f of x sine of nx dx. Okay, so these are the formulas that we have. Now see our function. What is f of x? So let us try to simplify this f of x first. Okay, so first of all, we need to understand what f of x is, and then we are able to find out this integrals a0. Okay, now we have f of x is equal to square root of 1 minus cos x. So what we know is, since 1 minus cos of theta is equal to 2 sine square theta by 2. Okay. So we can write this as, this is square root of 2 sine square x by 2. And hence we can write this as root 2 sine of x by 2. So this is the function that we have. It is important to understand the function. Now we got this function, okay, and then we have to find out a0, an, and bn. So now let us find out this coefficients as we know the function properly. Okay, so consider, first we'll find out a0. So 1 upon 2 pi 0 to 2 pi f of x, that is root 2, and this is sine of x by 2 dx. So I can have this root 2 upon 2 pi 0 to 2 pi sine of x by 2 and dx. Then what we know is, we know integral of sine of ax plus b dx is equal to minus cos of x plus b upon a. So here in this case we have, is going to be, this is 2 upon 2 pi, and here we'll be having minus cos of x by 2 upon half, and this is 0 to 2. Now let us simplify this. So we have root 2 upon 2 pi, this is minus 2 cos of x by 2 and 0 to 2 pi. Okay, so this 2 and this 2 will get cancelled. I can have this 2 upon pi, and this is minus cos of x by 2, 0 to 2 pi. Let us apply this limit. So if I apply this limit, then what you'll get is 2 upon pi, then minus cos of 2 pi by 2, and minus minus plus, this is cos of 0. Okay, so this is equal to 2 upon pi minus cos pi plus cos 0. So what we know is, since we know cos of 0 is equal to 1 and cos of pi is equal to minus 1. So we apply this, and hence we get 2 upon pi equal to minus of minus 1 plus 1. So it is root 2 upon pi. This is 1 plus 1. So we can have 2 root 2 by pi. So here we got the value of a0. So we get this, we were calculating a0. So a0 is equal to 2 root 2 upon pi, and this is the equation. Okay, so once we get the value of a0, next we have to calculate the value of an. So now we have, okay, so an is equal to 1 upon pi integral 0 to 2 pi to sine of x by 2 into cos of nx. Okay. So we replace the value of f of x. The value of f of x is root 2 sine x by 2, and this is going to be cos nx. So I can write this as root 2 upon pi integral 0 to 2 pi sine of x by 2 into cos of nx. So what we know the formula for sine A cos B equal to half of sine A plus B plus sine A minus B. Okay. So using this formula here, we are able to get this is equal to 2 by pi integral 0 to 2 pi half of sine x by 2 plus nx plus sine x by 2 minus nx, and this is dx. Now let us simplify this. So we can have 2 upon 2 pi integral 0 to 2 pi, and here we have this term. So bring it here. It's going to be sine of, I can write this as half plus n into x plus sine of half minus n into x, and this is here. So this is equal to 2 upon 2 pi, and we have here 0 to 2 pi sine of, this we can write as 1 plus 2n by 2 x plus sine of 1 minus 2n by 2 x, and this is here. So moreover, we can simplify this as an is equal to 2 upon 2 pi integral 0 to 2 pi, and here I can write sine of n plus 1 by 2 x minus sine of n minus x by 2 x, n minus 1 by 2 x, and here dx. So what I know is I have taken this minus sign out. So we know sine of minus theta is minus sine theta, and that's why I have taken this minus out. And now let us integral. So sine of the integral of sine is going to be cosine minus cosine precisely. Okay. So this is equal to, this will be 2 upon 2 pi, and here we have minus cos of 2n plus 1 by 2 into x upon 2n plus 1 by 2. Whatever the coefficient of x that we have to take here. This will be minus minus plus, and this term will be cos of 2n minus 1 by 2 x, and here we have this is 2n minus 1 by 2, and here we get this limits from 0 to 2 pi. Okay. So now let us apply these values. So I can write this equation as root of 2 upon 2 pi, and this is, I'll write minus 2 upon 2n plus 1 cos of 2n plus 1 by 2 into x plus, this is 2 upon 2n minus 1, and here we get cos of 2n minus 1 by 2 into x, and this is 0 to Okay, so here I'd like to add one deduction to the question that we have. Okay, hence find summation n running from 1 to infinity 1 upon 4n square minus 1. Okay, that will add to this question. So we'll find that also. Now, what we can have is, see here, let us apply these limits. So we can have, this is root 2 by 2 pi, and now minus 2 upon 2n plus 1, and this is cos of. Okay, see, I am applying 2 pi, so I'll be having this term is equal to 2n plus 1 into pi. Because x is equal to 2 pi, this 2 and the 2 from the 2 pi will get cancelled, and we'll be having this term. So here we'll have 2 upon 2n minus 1, and this is cos of 2n minus 1 pi. Now apply the lower limit 0. So minus minus will become plus 2 upon 2n plus 1, and this is cos of 0. This will become minus 2 upon 2n minus 1, and this will be cos of 0. Okay. Now we have to think that what is cos of 2n plus 1 pi, and this cos of 2n minus pi will be. Okay. So one thing you need to understand here, so whether it is cos of 2n plus 1 or whether it is cos of 2n minus 1. So anyhow, this cos of this term 2n plus 1 and 2n minus 1 will be odd term. Okay, and hence the value of cos is going to be minus 1. Okay, so what we can have is having, since 2n plus or minus 1 is odd always, this number will be odd always, and hence cos of 2n plus or minus 1 pi is equal to minus 1. Okay, because cos of 2n pi is going to be 1 and cos of pi is going to be minus 1. So this always will be a minus 1 term. And hence, this is going to be minus 1, this is going to be minus 1. Cos of 0 we know. Also, cos of 0 is equal to 1. So we know cos of 0 is going to be 1, and these terms are going to be minus 1. So we can write this as n is equal to root 2 upon 2 pi. This is minus 2 upon 2n plus 1 into minus 1 plus 2 upon 2n minus 1 into minus 1, this term, plus 2 upon 2n plus 1 is going to be minus 2 upon 2n minus 1. Okay, let us simplify this term. So it is root 2 upon 2 pi. This minus minus will become plus. So 2 upon n plus 1. This will become minus 2 upon n minus 1 plus 2 upon n plus 1 minus 2 upon n minus 1. Now we can see that this term and this term can be added, this term and this term can be added. So we can have, this is equal to 2 upon 2 pi. This will be 4 upon 2n plus 1 minus 4 upon n minus 1. So you can have 4 common. So it is 4 root 2 upon 2 pi. And here we have 1 upon 2n plus 1 minus 1 upon 2n minus 1. So you can cancel 1 2 from here, and you'll be having 2 root 2 upon pi. This is 2n minus 1 minus 2n minus 1. And here we get this is 2n plus 1 and into 2n minus 1. So we can have 2 root 2 upon pi, and this 2n will get cancelled. So I'll be having minus 2 here, and this is 4n square minus 1. So we'll get a plus b and a minus b, so it will be a square minus b square. So we got this an is equal to minus 4 root 2 upon pi, and this is 4n square minus 1. So we got here the value of an, and hence we get n is equal to minus 4 root 2 pi into 4n square minus 1. So let's this next equation. And now we need to find the value of Pn, because we calculated A0, we calculated An. Now it's time to calculate Pn. So let us calculate Pn. Now we have Pn is equal to 1 upon pi integral 0 to 2 pi or root 2 sine of x by 2, and we have sine of nx, and this is dx. Okay, so I can again write this as 2 upon pi 0 to 2 pi sine of x by 2 into sine. Now we know the formula. This is the formula. So we have sine A got here cos of A minus B minus cos of A plus B. So we have to use this formula, and then we get here as this is equal to 2 upon pi integral 0 to 2 pi half of cos of x by 2 minus nx plus cos of x by 2. Here you will have minus. So minus cos of x by 2 plus nx, and this is here. So we can have this as 2 upon 2 pi integral 0 to 2 pi, and we have cos of half minus n x minus cos of half plus n into x, and here we have, please use proper brackets so that you will not have any trouble anywhere. So you will be having 2 upon 2 pi, then integral 0 to 2 pi. Here we have cos of 1 minus 2n by 2 2x minus cos of 1 plus 2n by 2 into x and dx. We know the integral, so this is bn. So we know the integral bn is equal to root of 2 upon 2 pi, and here we'll have sine of 1 minus 2n by 2 x upon 1 minus 2n by 2 minus sine of 1 plus 2n by 2 x upon 1 plus 2n by 2, and the limits are 0 to. So we simplify this as 2 upon 2 pi, and this is 1 minus 2n by 2. So here I'll be having the reciprocal, and so we can have 2 upon 1 minus 2n sine of 1 minus 2n by 2 x minus 2 upon 1 plus 2n and sine of 1 plus 2n by 2 and x. The limits are 0. So now we have to be careful here. See the limits. The limit is going to be 2 pi. So if I put 2 pi, this will be a odd multiple of pi. So sine pi is 0. If I put here 0, then sine 0 is 0. So what we can say is, since sine of n pi is equal to sine of 0 is equal to 0, hence we have n is equal to, because here we will get sine of n pi and sine of 0. So both the terms are going to be 0. So we can say this entire Bn is going to be 0. So now we know the value of An. We have calculated the value of An. Also we have calculated the value of A0. Okay. Once we know the value of A0, we know the value of An, and hence using these values in equation 1, we are able to write the Fourier series. Okay. So let us write the Fourier series that we have obtained. Okay. And hence we say, from equation 1, 3, and 4, we get. Okay. So what we get is f of x is equal to, so it is 2 root 2 by pi minus 4 root 2 by pi summation n running from 1 to infinity 1 upon 4n square minus 1, and we have cos of nx. So we can write this as root of 1 minus cos x is equal to 2 root 2 upon pi minus 4 root 2 upon pi, and here we have summation n running from 1 to infinity 1 upon 4n square minus 1 into cos of nx. This equation 5. Now see the claim what we want to prove. Okay, so we have a claim to prove. Let us see what is the claim. The claim is that we want to find out the value of this series 1 upon 4n square minus 1. Okay, so where do we can see this series in the final expansion? So you can see this is the series I want. Okay, and if we want this series, then this term has to be 1. So when it is possible that cos of the term is going to be 1 for all n, so it is easy that if I put x is equal to 0, then only it is possible that this term will be all cos 0, and so it will be 1. And hence what we do is put x is equal to 0 in above equation we get. Okay, so what we are able to get is, see, if I put cos of 0, so cos of 0 is going to be 1. So this term is going to be 0. Then it is 2 root 2 upon pi minus 4 root 2 upon pi. And then this term is n running from 1 to summation n running from 1 to infinity 1 upon 4n square minus 1. Cos of 0 is going to be 1. Okay. Now, what we can do is take this on the other hand side. So you can have, this is minus 2 root 2 upon pi is equal to minus 4 root 2 upon pi and summation n running from 1 to infinity 1 upon 4n square minus 1. Now what you can cancel? You can cancel minus sign, you can cancel see, you can cancel pi, you can cancel minus 2, and you can cancel root 2 also. So you get 1 is equal to twice summation n running from 1 to infinity 1 upon 4n square minus 1. Or we can write this as this is half equal to summation n running from 1 to infinity 1 upon 4n square minus 1. Or we proved that summation n running from 1 to infinity 1 upon 4n square minus 1 equal to. This is how we are able to prove claims using the Fourier series. Now, do you have any doubt this example? If you have any doubt, you can ask, please. Okay, so that's fine. Shall we go for the next? Yeah, there is no doubt. That's good. So we'll go for the another example. Okay, so let's go for another example. That's good. Okay, so we'll try here the next example. Find Fourier series expansion for f of x is equal to x, 0 less than or equal to x less than or equal to pi, and this is 2 pi minus x, pi less than or equal to x less than or equal to. Okay, so that's what we have. Now we want to find the Fourier series expansion for this function. So we go with the solution. Let f of x is equal to x, 0 less than or equal to x less than or equal to pi, and this is equal to 2 pi minus x, pi less than or equal to x less than or equal to b. Find in 0 to 2 pi. Okay, so this function is defined in 0 to 2 pi. Then we have L is equal to 2 pi and hence L is equal to pi. Now we have the Fourier series expansion for this. The Fourier series expansion of f of x given as. So what we have, f of x is equal to a0 plus summation n running from 1 to infinity an cos of nx plus summation n running from 1 to infinity en sine of nx. That is equation 1, where a0 is 1 upon 2 pi integral 0 to pi f of x dx. An is equal to 1 upon pi 0 to 2 pi f of x cos of nx dx, and En is equal to 1 upon pi 0 to 2 pi f of x sine of nx dx. Okay, so that's what we have. Now let us simplify this one by one. Okay, so first we consider a0 1 upon 2 pi 0 to 2 pi f of x dx. So here we need to see that the function is defined as x from 0 to pi and 2 pi minus x from pi to 2 pi. So we have to split this integral into two parts as this is equal to 1 upon 2 pi integral 0 to pi f of x dx plus integral pi to 2 pi f of x dx, and that is equal to. So what we get here 1 upon 2 pi integral 0 to pi x dx plus pi to 2 pi 2 pi minus x dx. Okay. So let us find the integral. It's easy. So we can have 1 upon 2 pi, and then here we have this is x square by 2 from 0 to pi plus this is 2 pi x minus x square by 2 from pi to 2 pi. Now this is 1 upon 2 pi. If I put here pi, then it will be pi square by 2 minus the lower limit 0 plus here if we put 2 pi, then this will become 4 pi square minus 4 pi square by 2, then minus here will be having 2 pi square and minus minus will become plus pi square by 2. Okay. So this way we have limits here. Now simplify this. So 1 upon 2 pi, here I'll get pi square by 2 plus. So this is what we can have is 4 pi square minus 2 pi square minus 2 pi square plus pi square by 2. And this is what we'll get is 1 upon 2 pi. So I'll be having pi square by 2. This will get cancelled and you will be having plus pi square by 2. So we have 1 upon 2 pi into pi square and this will become pi by 2. 1 pi will get cancelled. So we get here a0 is equal to a0 is equal to pi by 2. So this is the next equation. Now we have to think of the an. So we can have for an. Now we have an is equal to 1 upon pi integral 0 to pi x into cos of nx dx plus we'll have pi to 2 pi 2 pi minus x into cos of nx dx. Okay, and hence we have to use here by parts rule. So this is going to be u and this is v. For this integral, this is u and this will be v. Now using generalize by parts. We get, so what we are able to get here, an is equal to 1 upon pi. Okay, so let us see for the first integral. X as it is, the integration of cosine, that's what we'll be having, sine of nx upon n minus the derivative of x is going to be 0. The integration of this is minus cos of nx upon n square, and the limit is 0 to pi. Now plus. Okay, so think of this integral. So we have 2 pi minus x, and the integral will be sine of nx upon n minus the derivative of this term will be minus 1, and the integration of this is minus cos of nx upon n square, and here we have the limit pi to. Please be careful while writing the brackets and limits. Okay, so what we have here, we know since sine of n pi is equal to sine of n pi is equal to sine of 0 is equal to 0. So here you will get sine of 0 and sine of n pi. Here you will get sine of n pi and sine of 2n pi, and that all terms are going to be 0. We can write hence we have what will be having an is equal to 1 upon pi. Here we get this minus minus plus cos of nx upon n square. This is 0 to pi, plus we have this will be minus minus minus, so minus cos of nx upon n square, and this is pi to pi. Okay, now let us apply these limits. So we got 1 upon pi. Here if I put this pi, then I'll be having this is cos of n pi upon n square minus cos of 0 on n square. Then this will be minus cos of 2n pi upon n square and minus cos of n pi on n square. Okay, so here I have taken this minus outside. So this is the upper limit minus this is the lower limit. Simplify this 1 upon pi. Now cos of n pi is minus 1 raised to n upon n square minus 1 upon n square. This is minus 1 upon n square, and minus minus plus 1 upon minus 1 raised to n upon n square. So what we know is, we know that cos of 0 is equal to 1, cos of n pi is equal to 1, and cos of n pi is equal to minus 1 raised to n. Now simplify this. So we get an is equal to 1 upon pi. So we can have twice minus 1 raised to n minus 2 upon n square. So we get here an is equal to 2, and here we get minus 1 raised to n minus 1 upon n square pi. Okay, so here we have to be careful that this value depends on n. Okay, so whenever you get these terms, okay, if we have minus 1, 1 plus or minus 1 raised to n, or minus 1 raised to n plus or minus 1, then check for n even and n. So we have to, when you will get these terms, 1 plus or minus 1 raised to n, or minus 1 raised to n plus or minus 1, then we have to check for what will happen if n is even and what will happen if n is odd. So here we have that situation, and hence we have to consider what if n is even, what if n is odd. So if n is even, then minus 1 raised to n is equal to 1. So this term becomes 1, 1 minus 1 is going to be 0, and hence an is equal to 0. If n is odd, then minus 1 raised to n is equal to minus 1, and hence an is equal to. So this will be minus 1, minus 1, minus 2, and this term will be minus 4 upon n square y. So this whole equation is 3. Now we calculated A0, we calculated AN. Now we have to calculate what happens to BN. Okay, so we got here A0, we got AN. So let us calculate BN. Okay, and hence we have En is equal to 1 upon pi integral 0 to pi x sine of nx dx plus integral pi to 2 pi minus x into sine of nx dx. So again we'll be having u, and this is v. This is going to be u, and this is going to be v. So we have to apply by parts, generalize by parts rule. So we can say, using generalize by parts rule, we get, so what we are able to get is En is equal to 1 upon pi. And for the first integral, we have x. This is minus cos of nx upon n, and then will be minus 1, and this is minus sine of nx upon n square. The limits are 0 to pi. Plus, now for this integral, it will become 2 pi minus x into minus cos of nx upon n, minus the derivative is minus 1, and you'll be having here minus sine of nx upon n square, and this is 0. Now we have to apply the limit. So what we can say is, since sine of 0 is equal to sine of n pi is equal to sine of n pi is equal to 0, and hence we have, what will be having, En is equal to 1 upon pi. Here we have minus x cos of nx upon n. This is 0 to pi. This term will be plus 2 pi minus x minus cos of nx upon n, and this is pi to 2 pi. That's what we have. Now let us apply the limits. So this is equal to 1 upon pi. For the first integral, what will be having? Minus pi cos of n pi upon n minus minus plus 0, because we have x here. So this term is going to be 0 plus. For this integral, 2 pi minus 2 pi is going to be 0. Then we're having minus.
Sir, the screen is not visible.
Screen is not visible.
It is visible, sir.
It is visible, sir.
Okay.
Sir, it's visible.
Sir,
Okay.
it's visible.
Okay. Okay. So here, if I put 2 pi, then this 2 pi minus 2 pi will be 0. So this term is going to be 0. Now, what happens to pi? So if I want to use pi, then this will be 2 pi minus pi. So it will become pi. And here, this is going to be minus cos of n pi upon n. Okay. And that's what we'll be having here. Okay. So simplify this. 1 upon pi. Then this is minus pi minus 1 raised to n upon n. So this minus and this minus will become plus, and we have pi into cos of n pi upon n. So this cos of n pi is again going to be minus 1. So I can write directly here. This is going to be minus 1 raised to n. So you can see this is minus term, this is plus term, so this has to be 0. So we got here that Bn is equal to 0, and hence we got Bn is equal to 0. So this next equation. So we can see that we got the value of An, we got the value of A0, okay, and hence we are able to write the Fourier series. So A0 is going to be pi by 2, An is going to be minus 4 upon n square pi, okay, and Bn is 0. So we can write the Fourier series. So we can write from equation 1, 2, 3, and 4. We have f of x is equal to, this is pi by 2 minus 4 upon pi summation 1 upon n square cos of mx. Okay, now here you cannot write directly n running from 1 to infinity. So here this exists only for n odd. Okay, so you can see that this an exists only for n odd. So we have to be careful here. This exists only for n odd, and hence we have to, while writing the final answer, we have to mention that n is odd. And if you do not mention n is odd, that means you are writing the unnecessary term which does not exist. Okay, and or this expression you can write as, okay, since n is odd, we can write as, okay. So remember this thing. 2n is even and 2n minus 1 is odd. So this is always even, this is always odd, and I want this term to be odd. Okay, so if I want this term to be odd, then this term inside the summation should be replaced. Okay, and this term will be also replaced. So we write this as f of x is equal to pi by 2 minus 4 upon pi summation. Now I am writing n running from 1 to infinity, but inside the summation I am writing 2n minus 1 bracket square into cos of 2n minus 1 x. Okay, and if you put the value of n1 to infinity here now, it will give you the same expression. So that's why we have to be careful. Here I am writing n is odd, and here I am writing n is running from 1 to infinity. But when I am writing n is running from 1 to infinity, inside the summation I am replacing n by 2n minus 1, which is an odd term always. And here when I am writing n is equal to odd, then I am not replacing anything. So both these expressions are correct. Okay, and that's why we have to be careful. When we write n is odd, this is the expression. When you write n is running from 1 to infinity, this should be the expression. Okay, so that's how you have to be careful while writing the Fourier series. Okay. Now, do you have any doubt in this example? Okay. Is there any doubt in this example or the previous example? Okay. That's great. Good. Okay. Okay.